Hi everybody. In the previous video, we introduced entropy from kind of a conceptual standpoint. In this video, we'll see how entropy plays out for a variety of macroscopic systems, and we'll also talk about what the second law of thermodynamics says about entropy. As we said at the beginning of the previous video, the spontaneity of chemical processes depends on both the tendency for energy to be minimized, so systems tend to move toward their energetic ground states, and also the tendency of systems to become more disordered, to have macrostates that correspond to larger numbers of microstates. We already have state functions that quantify the energy of a system, both the internal energy U and the enthalpy H. But we don't yet have a state function that quantifies disorder, and that's what we're going to talk about now. The textbook begins to motivate this state function that quantifies disorder by assuming that it relates to the heat added to a system, Q. This line of reasoning seems a little bit contrived to me, but it will lead us to the definition of entropy in a logical way, so I'll follow the same line of reasoning. To motivate our definition of this state function, I'll use an ideal gas as an example. We're going to start by thinking about Q reversible, the amount of heat transferred to a system in a reversible process, even though we know from our past discussion of the first law of thermodynamics that heat itself is not a state function. Because heat is not a state function, we can write the differential amount of heat as delta Q, an inexact differential. But let's think about why delta Q is an inexact differential. From the first law of thermodynamics, which tells us that Q equals delta U minus W, we can take the differential of that and say that delta Q equals du minus delta W. Notice that because U is the only one of those that's a state function, it's the only one that's written as an exact differential. We can rewrite both of these terms. We can write du as the heat capacity times dt, just from the definition of heat capacity, and we can rewrite minus delta W as plus PdV, because that's our definition of pressure volume work. We can then replace the pressure term with nRT over V from the ideal gas law. Let's look carefully at these two terms on the right. The first term, heat capacity times dt, is an exact differential. And we can see that because the entire term is expressed in terms of temperature. There are no other variables in that first term, meaning that we can integrate that term as normal regardless of what the conditions are. But the second term, nRT over V times dV, is an inexact differential. And we can see that because the term not only has the variable volume, but it also has a temperature in there. Meaning that if we were going to integrate this last term, the value we would get would depend on what the temperature was. In other words, it would depend on path, meaning it's not the differential of a state function. So, because one of these terms is an inexact differential, we know that delta Q is an inexact differential and heat is not a state function. But we already knew that, so why am I telling you this? I'm telling you this because expressing delta Q in these terms gives us a big hint about what we can do to make this a state function. Suppose we took this entire equation and divided by temperature. Now we have delta Q reversible over temperature equals both the first and the second terms over temperature. So heat capacity dt over temperature plus nR dV over volume. Now both of these terms are exact differentials. The first term is only in terms of temperature, and the second term is only in terms of volume. So we can integrate both of those terms as normal, and we'll get the same answer regardless of what the conditions are. So that means that even though delta Q reversible is an inexact differential, delta Q reversible over the temperature is an exact differential. And we're going to define that exact differential as ds. Now we use a d because this is a differential of a state function S. That's our definition of entropy. So this is how we've defined entropy, such that its differential is delta Q of a reversible process divided by temperature. In deriving this definition of entropy and thinking about why it's a state function, we were looking specifically at an ideal gas, but it turns out that this definition of entropy is general. We're now going to look at some changes in the pressure and volume of an ideal gas to not only confirm that it's a state function, but to also give us some practice thinking about how to calculate changes in entropy in a pressure-volume diagram. The processes that we're going to look at are these. In both cases, we're going to start at the point in the top left corner of the pressure-volume diagram, labeled V1, T1. And we're going to take two different paths to the point labeled V2, T1. First, we're going to look at an isothermal expansion, where the temperature stays the same the whole time. And then we're going to look at an adiabatic expansion step, followed by constant volume heating. Because both of these paths, the red path and the blue path, start and end at the same points, and we know that entropy is a state function, it must be true that the changes in entropy are the same along both paths. We're going to confirm that. I'll make the pressure-volume diagram a little bit smaller so we have some room to do math. And before calculating changes in entropy, I want to remind us that we know that the heat and the work of these two different paths are actually different from each other. Work is equal to the negative area under the curves, and you can see that those negative areas are different for the red and the blue paths. And because the work is different, the heat must also be different. But even though the heat and work are different for those two paths, we know that because entropy is a state function, delta S must be the same. Let's look first at the red path, the isothermal expansion of an ideal gas. We'll start from the first law of thermodynamics, which tells us that for any path through a pressure-volume diagram, du equals delta Q plus delta W. We'll choose to think about this as a reversible path, so it's easier for us to keep track of heat and work. Because we're looking at an ideal gas, and the internal energy of an ideal gas depends only on temperature, we know that for an isothermal process like this one, du has to be equal to 0. So we can rearrange the first law to say that delta Q reversible equals minus delta W reversible. We can then substitute in PdV for minus delta W reversible, and then we can use the ideal gas law to replace pressure with nRT over V. So we now have an expression for delta Q reversible. And given our definition for ds at the top of the slide, we can say that delta S, the finite change in entropy, is equal to the integral of delta Q reversible over temperature. We have an expression for delta Q reversible. We said that that's equal to nRT dV over V. So if we take that expression and divide by temperature, we can put inside this integral nR dV over V. N and R are just constants, so we can take them out front of the integral. And now we just have to integrate dV over V from volume 1 to volume 2. That, as we've seen before, is equal to the natural log of V2 over V1. So, we've looked at a reversible isothermal expansion of an ideal gas and found that the change in entropy is nR times the natural log of V2 over V1. Because entropy is a state function, we know we're going to find this same value of delta S along the blue path. But we're going to look at the blue path anyway to give us some more practice. So let's remember this value, nR times the natural log of V2 over V1, because we're going to see it again soon. The blue path has two steps. It's an adiabatic expansion of a monatomic ideal gas, followed by constant volume heating. If we want to know the total delta S, we need to find delta S along each of those two steps. The first one is easy. The definition of an adiabatic expansion is that there's no heat transfer. And you can see that our definition of differential change in entropy is differential heat transfer divided by temperature. So if there's no heat transfer, then regardless of what the temperature is, there's never any change in entropy. So for any adiabatic step, we can always quickly say that there's no change in entropy. For the second leg, it's going to be a bit trickier to find the change in entropy. We'll start from the definition of constant volume heat capacity by saying that du equals the constant volume heat capacity Cv times dt. And we'll also use the first law of thermodynamics, which tells us that du is also equal to delta Q reversible plus delta W reversible. This second step in the blue path happens at constant volume. There's no change in volume, and therefore there's no pressure volume work, so we can ignore the delta W term. That means we have an expression for delta Q reversible in terms of heat capacity. At this point, let's remember a couple of results that we've seen before, so we don't have to reinvent the wheel. First of all, remember that in a previous video, we looked at the adiabatic expansions and compressions of monatomic ideal gases and found the relationship between the initial and final temperatures. We found this expression T2 equals T1 times the ratio of volumes raised to the 2/3. That's a result that we've already shown. We've also shown in our coverage of statistical mechanics that the constant volume heat capacity of a monatomic ideal gas is 3/2 nR. That comes from the fact that a monatomic ideal gas only has translational modes. So we can use these two previous results to find the change in entropy. Based on our definition of ds, we can say that delta S equals the integral of delta Q reversible over temperature. We have an expression for delta Q reversible for this case. It's the constant volume heat capacity times dt. So if we take that quantity and divide by temperature, we can say that delta S is the integral from the initial temperature to the final temperature, and note that in this second step the initial temperature is T2 and the final temperature is T1. And this is the integral of Cv dt over the temperature. We can substitute in 3/2 nR for Cv, and because those are all just constants, we can take them out front. And we know that the integral of dt over t is just the natural log of the ratio of temperatures. Finally, if we want to express this in terms of volumes rather than temperatures, we can use the result on the second to last line of this slide, where we can relate the ratio of temperatures to the ratio of volumes. Instead of T1 over T2, we can write a ratio of volumes, V2 over V1 raised to the 2/3 power, and when we have the natural log of something raised to the 2/3, we can bring the 2/3 out front where it's going to cancel with the 3/2, and we can find that delta S for this second step, and therefore for the entire blue path, is nR natural log of V2 over V1. Notice that this was the same result as we found for the red path, which it had to be, because entropy is a state function. So at this point we've defined entropy such that it's a state function, and we've confirmed for a particular case that it is in fact a state function. Next, we're going to talk about what the second law of thermodynamics tells us about entropy. One common statement of the second law is that the entropy of an isolated system, one where energy does not go in or out, and this isolated system could be something that's small or it could be something as big as the entire universe. The entropy of an isolated system spontaneously increases over time. Let's look at an example that illustrates why entropy increases spontaneously. In this example, the isolated system we're going to look at is a box with two sides, a hot side and a cold side. The hot side is at temperature TH and has volume VH, and the cold side has temperature TC and volume VC. This is an isolated system, so no energy is going in or out of this box as either heat or work. For simplicity, the volume of each side of this box is constant. And although no energy is going in or out of the box as a whole, energy can flow from the hot side to the cold side as heat, so the two sides are in thermal contact with each other, and heat can and does flow spontaneously from the hot side to the cold side. So our question is, how does the total entropy of the box change? We'll start off by recognizing that on each side of the box, the first law of thermodynamics holds. So as energy is transferred from one side to the other, the change in internal energy has to reflect the changes in heat and work. Because we said the volume of each side of the box is constant, we can ignore the work term and say that du is equal to delta Q on each side. We've defined the differential change in entropy ds as delta Q over T, so we can say delta Q on each side of the box is equal to the temperature on that side of the box times the differential change in entropy. Now we can rearrange these equations to isolate entropy and say that on each side of the box ds is equal to du over the temperature. To anticipate the next step, I'm going to make one more substitution and recognize that duc, the change in internal energy of the cold side of the box, has to be equal to minus duh, the negative change in internal energy of the hot side of the box. In other words, because we said the box as a whole is an isolated system, we know that any internal energy gained by the cold side of the box has to be lost by the hot side of the box. We're interested in the total change in entropy when heat is transferred. So the total change in entropy of the box is going to be the sum of the changes in entropy of the hot side and the cold side, dSH plus dSc. And we can substitute in for dSH and dSc the expressions that we just found, and find that the differential change in entropy of the whole box is du of the hot side, the change in internal energy of the hot side, times the difference in the reciprocals of the temperatures, 1 over Th minus 1 over Tc. Remember, we were trying to illustrate that this entropy is increasing over time, so let's think about what the signs of these different terms are. DUH is the differential change in internal energy of the hot side of the box. The hot side of the box is having heat transferred away from it spontaneously, because heat flows from hot to cold. So the internal energy of the hot side of the box is decreasing, and DUH must be negative. If we look at the second term, we know that TH, the temperature of the hot side of the box, must be higher than TC, the temperature of the cold side of the box, almost by definition. So 1 over a larger number minus 1 over a smaller number is going to be negative, assuming those two temperatures are different. So if TH and TC are different from each other, the change in entropy is going to be a negative number times a negative number, which is a positive number, as we expected to find. Entropy increases spontaneously. So let's review what we can conclude from this example. We've seen that if a system is not in thermal equilibrium, in other words, if heat is being transferred from a hotter side to a colder side, then entropy increases spontaneously. This is what we call an irreversible process. Once entropy increases, it can't come back down. If we were looking at the limit where the two temperatures, TH and TC, were the same as each other, we would find that really nothing happens, no heat is transferred, and the entropy would stay constant. This is what's called a reversible process. When entropy stays constant, this is a process that could go in the opposite direction. So entropy increases in a spontaneous process, it stays the same in a reversible process, and it's impossible to have a process where the entropy of an isolated system decreases. At this point, I'd like to sum up where we are so far in our understanding of the first two laws of thermodynamics. Rudolf Clausius, who introduced the concept of entropy, posed this in a nice way. According to Clausius, the first law of thermodynamics tells us that the energy of the universe is constant. We could also say that the energy of any isolated system is constant. Although energy can be transferred within the system as heat or work, the total energy of an isolated system never increases or decreases. Within the system, energy is a zero-sum game. And the second law tells us that the entropy of the universe spontaneously increases and tends toward a maximum. Again, we could also pose this second law in terms of an isolated system, rather than the whole universe. As we've seen, in an isolated system, entropy stays constant in a reversible process, and it spontaneously increases in an irreversible process. Finally, I'd like to go through one more example that gets at some of the subtleties of thinking about changes in entropy of system versus surroundings. Here we show a reversible isothermal expansion of an ideal gas at temperature T from initial volume V1 to final volume V2. We've already talked in this video about the change in entropy during a reversible isothermal expansion. That was the red path in our first example. In that case, we showed that the change in entropy of the system was nR times the natural log of V2 over V1. Since we know that entropy is a state function, delta S can't depend on path. So any situation that starts at temperature T in volume V1 and ends at temperature T in volume V2 must have this same change in entropy, regardless of whether or not it was actually done reversibly. One implication of this is that if we want to find delta S, it often helps for us to choose a reversible path, because reversible paths make it the easiest for us to track transfer of energy. So even if a reversible path isn't actually what happens, we can think about something as a reversible path if we want to find delta S. With that in mind, let's think about this second situation. Here we again have an ideal gas that starts at temperature T in volume V1 and ends at temperature T in volume V2. But this time, it's not a slow, reversible expansion. It's a fast, irreversible expansion that happens when we poke a hole in the barrier of this box. But because the starting point and the ending point are the same, it must still be true that delta S of this system is equal to nr times the natural log of v2 over v1. So, because entropy is a state function, we know that delta S of the system has to be the same regardless of path. But we're saying that one of these situations is reversible and the other situation is irreversible. So what's different? Well, in the first case, we know that when the gas expands, W must be negative, which means that if the system is doing work on the surroundings, there must be a compensating amount of heat coming in from the surroundings to the system. So, because heat is being transferred to the system, the change in the entropy of the system, as we saw, has to be positive, but that means that the change in the entropy of the surroundings, from which heat is being transferred away, must be negative. Because the second law of thermodynamics tells us that the entropy of the universe doesn't change, so delta S of the universe has to be zero, that means delta S of the surroundings, the rest of the universe besides this ideal gas, has to be equal and opposite delta S for the system. So in this case, delta S of the surroundings has to be minus nr times the natural log of v2 over v1. Note that this negative change in entropy of the surroundings does not violate the second law of thermodynamics because the surroundings are not isolated. Energy can be transferred between the system and the surroundings. But the second situation is different. The surroundings, the rest of the universe outside the box, doesn't really care what happens inside the box because no work was done, so no heat was transferred. That means in this case the change in entropy of the surroundings is zero, and the change in entropy of the universe, the system plus the surroundings, is equal to the change in entropy of the system, nr times the natural log of v2 over v1. So, consistent with our previous discussion, in the reversible process, the change in entropy of the universe is zero, and in the irreversible process, the change in the entropy of the universe is positive. Finally, just a few takeaway messages. Entropy is a state function whose differential we defined as ds equals delta Q reversible over T. The second law of thermodynamics tells us that the entropy of an isolated system, which could be the universe or could be some smaller isolated system, increases in a spontaneous process and stays the same in a reversible process. And we also saw that examples in which we try to find changes in entropy can involve sort of subtle considerations of system versus surroundings and reversibility versus irreversibility. That's all for now. In the next video, we'll look at the concept of absolute entropy and think about how it relates to the third law of thermodynamics.